I welcome you all to my lecture number 32 on digital signal processing, that is UEC 502 for electronics and communication engineering students and electronics and computer engineering students. Today we will discuss implementation of sampling rate conversion. For that we will discuss polyphase filters first. The polyphase structures for FIR filter are used for the efficient implementation of sampling rate conversion in different converters. The polyphase structure is based on the fact that any system function can be split as shown in equation A. That is, the system function of filter is hz, that is equal to summation n running from minus infinity to infinity hn z is from minus n. Now we will expand this series in a particular fashion. Now in this column, I will make the entries h0, h1, z is from minus 1 up to hm minus 1 raised to minus bracket m minus 1, and go on making entries in different columns like this. In this column, the entries are hm z raised to minus m, hm plus 1 raised to minus bracket m plus 1 up till h2m minus 1 raised to minus bracket 2m minus 1. So we have arranged the elements of this series in a particular fashion as shown in equation A. In each column, look at this. In each column, we have arranged the elements as shown in equation A. Now we can factor out the term z is from minus bracket I minus 1 at the ith row to obtain equation B. Now consider this row, first row, second row, and this is the last row. What I am going to do? I am going to factor out the term z is to a minus bracket I minus 1 at the ith row to obtain equation B. Like from this first row, I am taking out z is for 0. From this second row, I am taking out z is to minus 1 as a common factor. And from this row, I am going to take z is to minus m, z is to power minus bracket m minus 1. So what we have done, we can factor out the term z is to minus bracket I minus 1 at ith row to obtain equation B. Now look at this equation. A and B seems to be different, but the output, but they are equal to hz. Both are equal to hz, but they are just expressed differently. Now we can express the above equation B in a compact form as this equation. Hz is equal to summation I running from 0 to m minus 1, z is to minus I, pi, z is to m, mark it as equation C. And this is called M component polyphase decomposition. It's very simple that in equation A, I have arranged the elements of this series in a particular fashion in every column. And then I have taken out the common factor z is to minus bracket I minus 1 from the ith row to obtain equation B like this. And then I have expressed the equation B in a compact form as equation C, that is based on M component polyphase decomposition, that is hz is equal to summation I running from 0 to m minus 1, z is for I, p, I, z is for m, where piz is summation n running from minus infinity to infinity, h bracket nm plus I into z is for minus n, mark it as equation D. And this is polyphase component of hz. So piz is polyphase component of hz. Now from equation D, we can observe that each subsequence pin with equal to hn capital M plus I, where I is changing from 0 to m minus 1. So piz is equal to summation n running from minus infinity to infinity. This is pin, z is from minus n. where PIN is equal to Hn capital M plus I. So we can observe that each subsequent PIN can be obtained by downsampling a delayed or phase shifted version of the original impulse response Hn. Now to develop an M component polyphase filter structure, we can represent the Z transform of output sequence as YZ is equal to HZ into XZ. So if the input to the system is, input to the filter is Xn, its Z transform is XZ. The system function of filter is HZ. Now the output will be YZ is equal to HZ into XZ. This is what we have done in earlier lectures also. So now instead of H, Z, I will substitute equation C based on M component polyphase decomposition here and expand it, and I will find that P naught Z raised to power M into XZ plus P1 Z raised to power M into XZ into Z raised to power minus 1 plus P2 Z raised to power M XZ Z raised to power minus 2 plus so on. Mark it as equation E. Now, same equation I can express in a different way. That is P naught YZ is equal to P naught Z raised to power M XZ plus I am taking out Z inverse from the rest of the terms, that is P naught Z raised to power M XZ plus Z inverse bracket P1 Z raised to power M XZ plus Z inverse P2 Z raised to power XZ and so on, and mark it as equation G. Mark it as equation G. The both equations convey the same output YZ, but when we are going to implement, when we will implement these equations in terms of structures, then based on equation E, we will have this structure, and based on equation G, we will have this structure. So let us see. This is equation E. The equation E results in the following polyphase structure for M is equal to 3. I've considered M is equal to 3 for simplicity. I just want to give you an example. So input is Xn, whose Z transform is XZ. So first term is P naught Z raised to power M is equal to 3, P naught Z raised to power 3 XZ. So plus P1 Z raised to power 3 XZ Z raised to power minus 1 plus P2 Z raised to power 3 XZ Z raised to power minus 2. So this is the structure corresponding to equation E. Now here it is XZ, here it is XZ Z into Z raised to power minus 1, here it is XZ into Z raised to power minus 2. Now this XZ is going to be multiplied by P naught Z raised to power 3, and then here we are going to add it, and like this we will do with all the blocks, and we will have YZ based on equation E. Similarly, based on equation G, that is equation G results in the following polyphase structure for M is equal to 3. Now YZ is equal to Z, YZ is equal to P naught Z raised to power 3 XZ plus Z inverse P1 plus Z inverse bracket P1 Z raised to power 3 XZ plus Z inverse P2 Z raised to power 3 XZ. And now first term is XZ into P naught Z raised to power 3, and then it is going to be summed. And then this term P1 Z raised to power 3 into XZ, P here XZ into P1 Z raised to power 3, and then it is going to be multiplied by Z inverse. And here it is XZ into P2 Z raised to power 3, and then it is multiplied by Z inverse, and then once more it is multiplied by Z inverse by this. So these all are going to be summed up here, and we will get YZ at output. That is YZ is equal to P naught Z raised to power 3 XZ plus Z inverse bracket P1 Z raised to power 3 XZ plus Z inverse P2 Z raised to power 3 XZ. So these two equations E and G are giving output Yn, but the difference is in their structure. The structure based on equation G is known as transverse polyphase structure. This is quite similar to the transverse FIR filter realization. These polyphase structures are valid for any FIR-IR filters and for any finite value of M. So we will use these two structures in lieu of HZ to reduce the computational complexity of overall multi-rate signal processing system. That is, to reduce the computational complexity of decimation process or interpolation process. Now, next is interchange of filters and downsamplers or upsamplers. In general, the order of a sampling rate converter, which is an linear time variant system, and a linear filter, which is an LTI system, cannot be interchanged. Now, it is clear that sampling rate converter is linear time variant system. Linear filter is linear time invariant system. So the order of a sampling rate converter and linear filter cannot be interchanged in a direct manner, but it is not impossible. Therefore, we take help of following two noble identities for swapping the position of a filter with a downsampler or an upsampler by appropriately modifying the filter. So if we want to swap their positions, we need to take help of two noble identities, but the changes need to be done, or the filter is needed to be modified if we want to swap the position of sampling rate converter and linear filter, then we must modify the filter. So we will discuss noble identities. For first identity, we recall that the input and output description of downsampler results in this. We will take help of this block now. So this xn is input. This is downsampling block, which downsamples the rate by a factor of d, and output of downsampler is v1m, and which is passed through a filter hz to give output ym. Now, as per the mathematical analysis or description of downsampler, and that results in yz is equal to 1 by d, summation I running from 0 to d minus 1 x bracket z raised to power 1 by d e raised to power minus j 2 pi I by d into hz. This is multiplication operator into hz. Mark it as equation J. This is based on the mathematical analysis of downsampling, which we have done in earlier lectures. Now, as we have done earlier, I express e raised to power minus j 2 pi I by d equal to w raised to power I with base d. Now we know that if this is the definition of e raised to power minus j 2 pi I by d, then w raised to power I d with base d is equal to 1. So what I will do, I will modify equation or express equation j in a different form, that yz is equal to 1 by d summation I running from 0 to d minus 1 x z raised to power 1 by d w raised to power I with base d into h z w raised to power I d with base d. Now here I can once more express yz as yz is equal to 1 by d summation I running from 0 to d minus 1 x z raised to power 1 by d w raised to power I with base d into h z raised to power 1 by d w raised to power I with base d, and this raised to the power d, this whole raised to power d, as shown on the screen. Now we can swap the position of these two terms, that yz is equal to 1 by d summation I running from 0 to d minus 1 h brackets z raised to power 1 by d w raised to power I with base d and whole raised to power d into x z raised to power 1 by d w raised to power I with base d. Mark it as equation K. Now, critically looking at equation K, we we are having a motivation to define V2Z dash is equal to HZ dash with raised to power D into XZ dash. That is, as motivated by equation K, I can define V2Z dash is equal to HZ dash raised to power D into XZ dash as shown on the screen. Now this V2Z dash can be further processed through a downsampler to give the same output VZ. So this gives rise to this block diagram. So by using equation K and by using the basic concept of downsampling, the following downsampling configuration comes into picture. Now we will compare these two block diagrams. Now we have done its mathematics above. And now this is based on the motivation received from equation K. That is, Xn is input. It is passed through a filter with response H, Z is for D, and output is V2N. And in Z domain, it is V2Z is equal to H, Z raised for D into XZ. And then it is downsampled D by a factor of D to give output YM. And you look at these two block diagrams, the output remains same, that is YM. So this means I can interchange or I can swap the position of these two blocks, but I need to make appropriate changes in the filter function. That's it. So this is called first noble identity used for downsampling or decimation related configurations to reduce the computation complexity. This is very important. Now we will discuss second identity. That's for second identity, we recall that the input output description of an upsampler leads to yn is equal to x n by I for n 0 plus minus I plus minus 2I plus so on and 0 otherwise. Now for the second noble identity, we use these two block diagrams. Now in the first block diagram, xn is input. This is passed through a filter hz, and the output is v1n, and which is upsampled to give output ym. So v1z is equal to xz into hz. It is very clear based on the signal system. And the yz is equal to v1z is for I based on upsampling mathematics equal to substitution of v1z here. Yz is equal to xz raised to power I, hz raised to power I, marked as equation L. Now we will handle the second block diagram. Here xn is input, which is upsampled by a factor of I, and which will give output v to m. So v2z is equal to xz is for I as per the mathematics related to upsampling. And v2m is passed through a filter with response hz is for I, and the output is ym. So yz is equal to xzi into hzi, marked as equation m. So if I look at the results, both block diagrams are giving the same output. So this means I can swap the position of the blocks provided that I make modification in the low pass filter as shown in these two block diagrams. So this is called second noble identity related to the upsampling or interpolation systems. It is clear that L and M represent two equivalent upsampling systems. So this is the second noble identity which will be used to reduce the computational complexity of the interpolation systems. The first noble identity is related to the decimation or downsampling. Second noble identity is related to the upsampling or interpolation systems used in multi-rate signal processing. Now it's possible to interchange the operation of linear filtering and downsampling or upsampling if we properly modify the system function of the filter. Now polyphase structures for decimation and interpolation filters. For decimation system, this is the conventional block diagram that xn is the input. It is passed through a pre-filtering structure HZ, that is anti-aliasing filter, and the output of anti-aliasing filter is Vn, and now Vn is downsampled to give output Ym. This block diagram P represents the conventional decimation system. Now I will use equation E for linear filtering and the downsampling the filter output by a factor D. Now let's have a look at first noble identity and equation E. So this is equation E. For m is equal to 3, I can express Hz in the form of, I can express Hz by using polyphase structure for m is equal to 3 here based on equation E. And the first noble identity gives us opportunity to swap the blocks in the blocks. The position of blocks can be interchanged, provided that we make appropriate changes in the system function of filter. So based on this, by using equation E for linear filtering and then downsampling the filter output by a factor D, we can show that the following structure serves the purpose for D is equal to 3. So I have replaced Hz with a polyphase structure here as shown above, and this structure Q is equivalent decimation system. The only change we have made, we have replaced Hz with a equivalent polyphase structure. Now I have considered D is equal to 3, that is downsampling factor is 3. Now Xn is input. Now it seems to be, the structure Q seems to be computationally if inefficient. In figure P, or block diagram P, the filter is operating at high sampling rate, Fx, while only 1 out of every D output samples is actually needed. This makes it an inefficient configuration. Now in figure P, it's quite clear that the filter is operating at high sampling rate. This filter is operating at high sampling rate Fx, while only 1 out of every D output samples is actually needed. This makes it an inefficient configuration. A logical solution is to find a structure where only the needed samples are computed by exploiting the concept of polyphase structures as shown in figure Q. By applying the first noble identity, we can modify the structure to give structure R. How? Using the first noble identity, I can interchange the position of these two blocks. So I can get this block here and this block here, provided that I make appropriate changes in this filter. So this leads to the new structure with D is equal to 3 like this. Now this structure R is computationally efficient and output is Ym. Now what we have done, we have replaced Hz with equivalent polyphase structure and then applied first noble identity to reduce the computation complexity. And in this filtering structure, only the needed samples are computed and all multiplications and additions are performed at the lower sampling rate Fx by D. An additional reduction in computation can be achieved by computing an FIR filter. An additional reduction in computation can be achieved by using an FIR filter with linear phase and exploiting the symmetry of its impulse response. This makes it an efficient structure. This is added reduction, but this structure gives a computationally efficient solution for the decimation process. But it is only possible with the help of first noble identity. Now we will go for interpolation system. The block diagram S shows the conventional interpolation system in which Xn is input. It is upsampled by a factor I and the output is Vm. And then we use post low pass filtering, which is through anti-imaging filter, which removes the images. And the output is Ym. Now by sampling the input signal by a factor I and then linear filtering the output by using equation G, we can show that the following structures serve the purpose for I is equal to 3. That is structure U. Now for that, we will have to look at equations, the polyphase structure based on equation G and the second noble identity. Now this is equation G, and this is the structure based on second noble identity. This structure is based on equation G. This structure is based on equation G. Now carefully look at this. So in that interpolation configuration, I will replace HZ with this polyphase structure. And we will take help of second noble identity like this. Now look at this. I can swap the positions of this block and this block, provided that I make appropriate changes in the system function of the filter. Now we will come back to the main article. Now I will replace HZ with the polyphase structure based on equation G. And this leads to the structure U. Now look at this, I is equal to 3, that is upsampling is taking place by a factor 3. And then instead of HZ, I am using a polyphase structure here. And the output is Yn. Now this is computationally inefficient structure. In figure S, the interpolator is realized by first inserting in this conventional system. In figure S, interpolator is realized by first inserting I-1 zeros between successive samples of Xn and then filtering the resulting sequence. The major problem with this structure is that the filter computations are performed at a high sampling rate, IFX. Here, IFX. A logical solution is to find a structure in which we first replace the filter by the transpose polyphase structure, as shown in figure U. Then we modify this structure by using the second noble identity to give the following configuration, in which all the filtering multiplications are performed at the low rate fx. So here I can apply the second noble identity. Now I can this upsampling block here and this filter block here by using second noble identity, and I will have resultant structure R. Now in this, all filtering multiplications are performed at a low rate fx. So this is computationally efficient structure. And thus, by using first noble identity and second noble identity, we can reduce the computational complexity of decimation and interpolation in the field of multi-rate signal processing in industry. So these two noble identities are very important, because by that I can swap the positions of filters and downsamplers or filters and upsamplers. And this has found a big application. Now this article is from the book of John G. Prokis on digital signal processing. This is your textbook. You can also consult S.K. Mitra's book, Digital Signal Processing, and other books shown in the reference books. That's all for today's lecture. Thanks for attending this session on DSP. See you in next lecture.